So today I'm going to talk about the Central Valley Project Improvement Act, and I don't know how many of you know what that is, but it's it was passed in 1992, and what it does is when power or water is purchased from the Central Valley Project, it takes a portion of those proceeds and puts it in a restoration fund, which is then split between programs that help restore anadromous fish in the Central Valley and water purchases for refuges to help migratory birds and other terrestrial species. So today I'm going to talk about the fish program side of that and how we're trying to restructure it to get a more science-based collaborative approach. So I am a biologist with the service. The CVPIA is a Department of Interior program that is jointly administered between the Fish and Wildlife Service and the Bureau of Reclamation. So it's a little bit unwieldy because we usually have, for every program within CVPIA, we have a service and a reclamation person that co-manage it or co-lead, and we have to split the money between the agencies. We went through a science review back in 2008, an independent review that said that's kind of a crazy way to do things. It's not very efficient. You should be more collaborative, more open and transparent, and have more of a science-based framework. And we agreed with all that, I think, with both agencies, but it's been really difficult to figure out how to restructure it to make it work better. So what I've been doing, I was given the task of figuring this out, so I've been writing an implementation plan to help do that. And this plan proposes a new framework for CVPIA that is intended to be more collaborative and science-based to restore native anadromous fish. And this is done using adaptive resource management. So adaptive resource management is like adaptive management but more structured. It's part of structured decision-making within a structured decision-making framework, if any of you know about that, and decision science. But it's a way to break down complex decisions, and then this special case, adaptive resource management, is when you make iterative decisions over time so that you can learn from a decision and improve your decision-making over time. So as part of this, you want to have quantitative predictions of the different actions you might do and be able to evaluate trade-offs between those. So we're developing a decision support tool to help us do that. And to make it all work, we have to revise the governance structure for the program. So right now, I'm acting as a science coordinator for fish programs to try to do that. We are creating, or in the process of creating, an integrated CVPIA fish program just called the Anadromous Fish Program. So if anyone's familiar with CVPIA, under the Act, there's all these different really tools that you can use to restore a fish. So it's, improve spawning and rearing habitat or do fish screens, these kinds of things. And those have become independent programs. So what we're trying to do is lump all those people together, all those programs together, and say, let's have a more flexible way of implementing the tools that we need and where we need to do them. And so we need to be able to manage this new process and then develop science-based priorities that are more landscape-based and on a 5-year time scale so that we can say, under CVPIA, we have this set of priorities, these types of tools, and this is where we want them done, and solicit proposals so that people can think, over the next 5 years, what types of projects might they propose implementing. So adaptive resource management, the key part of it are to set clear biological objectives. And you'll hear this again, I think, with John's talk next, is that one of the things we've really been trying to do in some of our bigger efforts in the Central Valley is to define what we mean by success. And so in the past, under a lot of these management actions, success might be how much gravel I added to a river, but that's not really success, right? Just because I put gravel in there, what does it really do? So we're trying to get back to those biological outcomes. So it's not successful for me to add gravel if I didn't end up producing more of what I wanted from the biological perspective. We need to be able to predict the consequences of our alternative management actions. So we need to know what actions are available to us and be able to predict what we think will happen if we implement them. and then have some kind of quantitative metrics so that we can evaluate trade-offs between implementing different sets of actions and then recommend what we think we should do. And then we need to monitor based on those predictions so that it doesn't help to say, I think I'll get more fish if I do this, but then you don't actually monitor that directly. So you need to have your monitoring plan match what you're predicting so that you can see what your outcomes were and then revise your conceptual or quantitative models over time. And we're trying to do all this within a collaborative and transparent process. So we don't want it to be internal just to our agencies or even to just the agencies, but opening it up to other stakeholders. So how do we implement it? This is what I've been struggling with for about the last year. We are modifying the organizational structure of the fish programs to work more effectively at a landscape scale. And that's tough because people tend to know their river and know what works in a particular place, but how do you scale that up? How do you think Central Valley wide? We want to integrate our restoration and planning efforts across agencies, so it doesn't really make sense to have CVPA have one set of goals where the NMFS recovery plan has another set and the state might have another set. So can we bring all of that together and say we're all working together to help restore native anadromous fish? Can we get all of our conceptual models to align and work within one framework? And then we want to engage, overall, we want to engage a broader community with interest in salmon restoration. So there's a lot of people doing great work. I work with Jeanette and Renee, and they're not within the agencies. I still want to tap into their knowledge and their resources so that we can all contribute to this broader goal. So this is how we're doing it. This is just a figure of how the organizational structure is working. So I'm now acting science coordinator. I'm in charge of putting together this science integration team. We just met for the first time last week. We had an informational meeting in September, and then Thursday and Friday of last week had a 2-day meeting where we really working meeting. And this team has technical representatives from all the agencies, so the service, reclamation, the state, DWR, and DFW, as well as NMFS, and then also representatives from all interested stakeholder groups, so water and power interests, as well as NGOs. And we are responsible as a team for coming up with a set of priorities for CVPIA. And we decided this would be on a 5-year schedule so that people weren't reacting to changing priorities every year, but would have some time to put some thought into projects. Our team is responsible for writing a 5-year plan on these priorities and giving it to the core team. The core team is a set of more policy-level representatives from the agencies. They will take that 5-year plan and issue a call for proposals. And then they'll reach out to both staff and CVPIA as well as stakeholders and watershed groups and say, here are our priorities for the program. Please submit proposals to us on how best you think you can implement those. Those proposals will then be ranked according to set criteria, and a set of recommended proposals will be put together as a CVPIA work plan and given to the regional directors of the service and reclamation, who are the implementing agencies. And then we also have, we plan to have an independent science review every 5 years who'll really be responsible for reviewing the science integration team part here, so the models that we put together in that approach. So this team is new, like I said. Right now we have about 20 members with the landscape perspective, so we want them to be able to think across the Central Valley and have a broad range of technical experience. So we want biologists, geomorphologists, modelers, statisticians, because we're putting together a pretty complex tool. It doesn't have to be super complex, but we want it to be sufficient to help inform our decision making. And so we don't want a whole room of fish biologists to do it. It includes agencies and stakeholders. And ultimately, they'll be recommending priorities for types of actions, so not do a gravel addition in this reach of this river, but more this watershed needs additional spawning habitat, or this, the upper Sacramento needs temperature controls, that sort of thing. And then they need to be able to reach out to additional technical staff with specific expertise when we need that. So this is what I've been showing at these meetings, and I don't need to go through all the things that the science team does not do, but like I said before, it's really difficult, I think, for people to move beyond how hard it is to implement a specific project to thinking more broadly. So this kind of spatial scale issue keeps coming up, and we keep addressing it, and I keep showing this slide, is that it doesn't matter if you think we can't do a big floodplain project on the lower Stanislaus. If that's what we need, that's what we recommend as a priority, and let people try to come up with solutions. So this is, when we did our decision support models, we started with this super complex, whiteboard of like, this is how the system works, and that's crazy. This is what's in people's heads. So we're trying to get that out into a model that we can actually look at different scenarios. So the decision support models are, there's a lot of consternation about them because they're never complex enough, but they're always too complex. How do you get that sweet spot where it's really helping you inform a decision without anybody relying on them completely? We're looking at them as tools. They're never supposed to be the end-all, be-all. We all have good brains where we can say this output doesn't make sense and this is why, I think, and modify it. But they're meant to predict outcomes of alternative actions so that we can look at trade-offs, and then once we implement something, we learn from it. So maybe it doesn't come out the way we thought, but that's useful information. We have draft DSMs available for every anadromous fish species for 26 watersheds, and now that team is working on revising the structure of the model and biological objectives, which are right here. So our main biological objective is the doubling goal for CVPIA, if you know what that is. It's double the populations of native anadromous fish on a self-sustaining basis. That is then further defined by looking at spatial structure, abundance, productivity, and life history and genetic diversity. And then this lower level here are all the metrics that we're coming up with that actually define these in the model. So things like the proportion of natural spawners versus hatchery, or the number of spawning populations per diversity group, that kind of thing. And this we're working on revising. This is actually outdated already because we changed it last week. And it's based on, our DSMs are based on a base population model. Again, this is already outdated because we are adding a delta piece and some other things. But basically, adults come back, some of them survive, they turn into escapees, some of them turn into fry. The fry either stay and grow, or some of them leave, and depending on survival, some of them turn into adults in the ocean. That's fairly standard. But then we have some consultants helping us to work on a tool where we can play around with some scenarios. So this is just a demo. This isn't actually what the model says right now, but in this dashboard, we're looking at Clear Creek. If you put in 10,000 adults from the ocean that are meant to go back to Clear Creek, how many do we think we get out? We think we get out 10,171 that end up back in the ocean. If we were to change to, let's see what I have, 20,000 right here, we still only get 10,171 adults predicted. So why would that be? We could change some of our parameters. If you were to double your spawning habitat, which is right here, right now it's at 1,300 units, say change that to 2,600, go back to 10,000 adults, you now get 28,000 in the ocean. So you can play around with this to say, what do we think is the most important thing to do in Clear Creek that we would predict would have the best outcome on all of our performance metrics from our objectives? So we have a set of deliverables that, at least right now, I'm responsible for, but really the whole team are doing. So this is the set of decision support models for all native anadromous fish species. We really want them to size our monitoring data so that we're only monitoring things that help us make better decisions, and again, used as a tool to inform priorities. We'll be producing an annual tech memo that documents updates to the model, and this is meant to be a living model, so it'll change over time depending on what we learn. And then a 5-year plan to recommend priorities for both types of projects and then also science and monitoring. So right now, the SIT's meeting through February. We're still working on the core team process for proposals, and then we'll start implementing. So thank you.